Assalamualaikum warahmatullahi wabarakatuh. So today in our airport design class, we will talk about geometric design of landing area part 1. The air side of an airport should have to accommodate the movement of the aircrafts. So when an engineer wants to design an airport was designed based on critical aircraft or design aircraft. So what is critical aircraft? Critical aircraft is the biggest size of aircraft that should have to be served by an airport which operated both landing or takeoff at least 500 times in an airport in a year. So, to make an airport easier to design, both ICAO and FAA classified the airport like this. So the ICAO classified the airport based on ARFL or Airport Reference Field Length and wingspan and outer main gear wheelspan. So ICAO have code number and code letter like here. So this is the classification of the airport by ICAO, and this is the airport classification by FAA. So the FAA classified the airport based on the maximum tail height or the critical aircraft with its tail height, wingspan and approach speed. So they have group number and category. So this is the airport classification by FAA. Basically, there are three most important parts when we want to design the geometric of landing area. In this semester, we will talk about geometric design of runway, geometric design of taxiway, and geometric design of apron. So this is based on the most important or the facilities in the airside. First, we will talk about the most important facilities for aircraft to take off or landing. The geometric design of runway. There are 11 parts that we will talk about in geometric design of runway. First is length of runway, width of runway, minimum distance between parallel runways, longitudinal slope, transverse slope, runway shoulder, runway strip, runway and safety area or RESA, clearways, stopways, and the last, runway turn paths. Nowadays, the length of the runway in each airport is different. It based on airport classifications which referring the critical aircraft or design aircraft. There are various factors that will affect the height of the runway, such as elevation above mean sea level, temperature, wind velocity, airplane operating weights, takeoff and landing flap settings, runway surface conditions like dry or wet, effective runway gradient, presence of obstruction in the airport, and any other restrictions. So, two organizations in aviation make some guidelines to calculate or determine the length of runway. So there are ICAO with its Annex 14 and FAA with its advisory circular. You can basically you can search the guidelines, or you can learn the guideline more in this. You can search it in Google and you can download it. First, the guideline to determine the runway length from IQ. Basically, because there are factors that may affect the length of runway, IQ made some correction for the runway length. Actually, I have explained to you before, so I will just recalling our memories. So the basic runway length will be multiplied by some corrections from elevation factor, slope factor, and temperature factor, and we will get the actual runway length. And this is how we get the correction from elevation, slope, and temperature. So this is how we calculate. Actually, we already discussed about it, so I will just skip this. And this is the example that we already discussed about it before, so I will just skip it. So the second one is FAA guideline to calculate the runway length. So basically, the FAA make the guideline based on aircraft performance curve. So the recommended runway length obtained for the weight category of airplane is based on using the performance charts. So we will look at the performance charts which published by the airplane manufacturers. For example, APMS. APMS is Aviation Performance Measuring System. So where do we get the charts or the performance curve? So we can contact the airplane manufacturer or air carriers for the information. So every aircraft has its performance curve and its difference for each aircraft. So make sure we can contact the airplane manufacturer to get the aircraft performance curve. And each airplane manufacturer's APM provides performance information on takeoff and landing runway length requirement. So basically we will have two kinds of aircraft performance curve. So the first is for takeoff and the second is for landing. And the airport designer will determine the separate length requirement for takeoff and landing. Then we will make an adjustment for the length, and then we select the longest length as the recommended runway length. So we will calculate, or we will know the length for takeoff, and the second we will know the length of runway when an aircraft landing, and then we compared we compared this, and we will choose the longest one. In aircraft performance curve before, we will determine the length of runway based on elevation. So how about the other factors? So the other factors, like there are other factors like temperature, effective runway gradient, and runway condition. So for the first is temperature. So the parameter airport temperature is used only for takeoff length determination by setting it equal to the mean daily maximum temperature of the hottest month at the airport. So the usually airport manufacturers will provide at least two takeoff runway length requirement charts. So for the first is at the SDT or standard day. So the standard day is in 59 degree of Fahrenheit or 15 degrees Celsius, and the other one or the second charts is for standard day temperature plus some additional temperature. For example, standard day temperature plus 27 degree of Fahrenheit or standard day temperature plus 15 degrees Celsius. So the second charts can use for the highest temperature. For example, we can use the second charts for the temperature 3 degrees Celsius. And also there are some additional temperature which is 3 degree Fahrenheit or 1.7 degrees Celsius. So if we have 89 degree Fahrenheit, we can still use the second charts. Basically, the second charts is just for the standard day temperature plus 27 degree Fahrenheit or for maximum 86 degree Fahrenheit, but in addition for the 89 degree Fahrenheit temperature can still use the second chart. And the second one is effective runway gradients. So the runway length for takeoff must be increased by 10 feet per foot of difference in centerline elevations between the high and the low points of the runway centerline elevations. And for the runway condition, the wet runway conditions are required only for turbojet powered airplanes. Now we will talk about the example how we use the FAA calculation method. So this is the data. So the design conditions is for we will make the runway for airplane Boeing 737-900 with mean daily maximum temperature of hottest month at the airport is 84 degree Fahrenheit and airport elevation at 1000 feet, and the maximum landing weight is like this, and this is for the maximum design takeoff, and there are maximum difference in runway centerline elevations 20 feet. So the maximum design landing weight and maximum design takeoff, we will get it from here, from the documents from the aircraft manufacturer. So for the Boeing 737-900, we will have the maximum design takeoff weight here, and we will get the maximum design landing weight here. So the first is we will determine the landing length requirement. So the Boeing 737-900 actually provides three landing charts. So the first is for flap settings 40 degrees, 30 degrees and 15 degrees. So we will just use the 14-degree flap setting landing chart like here. This is 40-degree flap setting landing charts. Why we choose this? Because it results in the shortest landing runway length requirement. So we will just compare for the 40, 30 and 15 degrees, and we choose the shortest landing runway length requirement. And for the flap 40 is it has the shortest landing runway length requirement. Then we will enter the horizontal weight axis at 146,000 pounds that we get before here. Then we proceed vertically until we get this curve. So there are the curve for dry runway here. So this is for the dry runway, and there are also for wet runway. And because the Boeing 737-900 is the turbojet aircraft, so we will use the wet runway. And then we should have to choose the wet runway here based on airport elevation. So because the airport is in 1000 feet, so and there is no 1000 feet here, we will just do some interpolation. So between the wet runway curve at sea level and wet runway curve 2000 feet, so we just get here. So for the sea level, the wet runway is here, this one, and for the 2000 feet airport elevation for wet runway is here. So we will use between the sea level curve and 2000 feet elevation here. So if we do interpolation, we will just get the point here, because our airport elevation is in 1000 feet. So then we proceed horizontally to the length axis here, and we will get around 6550, because this is 6000 feet and this is 7000 feet. So we will maybe have here 2,550 feet. Here we can use the interpolation also. So the length requirement is 6,600 feet. Why? Because we will round over to the next 100 foot interval. So from 6,550 feet will become 6,600 feet. So for the landing length requirement, we will get this. Next, we will calculate the takeoff length requirement. Next, we will calculate the takeoff length requirement. So this is the chart, and basically Boeing 737-900 APM will provide two kinds of the chart. The first is to calculate at the standard day, and the second is to calculate when the temperature is in standard day plus 27 degree of Fahrenheit, like this, because the given temperature for this example is 84 degree Fahrenheit. So we will use the chart that which has the standard day plus 27 degree Fahrenheit, like this, because it is less than 85.4 degree Fahrenheit, which is the maximum temperature of the hottest month at the airport required. So we can use this chart, the chart which has standard day plus 27 degree Fahrenheit. Then we will enter the horizontal weight axis at here 174,000 pounds, here, about here. Then we proceed vertically until we get this curve for the airport elevation corrections or airport elevation curve. So we have here sea level 2,000, 4,000, 6,000 and 8,000 feet, and because of our design, our airport design has 1,000 foot elevation, so we will just interpolate this between the sea level and between the curve for 2,000 airport elevation feet here. So between this curve and between this curve here, and we will just interpolate. Actually linear interpolation between elevations is invalid because the application of the takeoff chart is for airport design and not for flight operations, so the interpolation is allowed. Then after we get the interpolation, we proceed horizontally to the length axis. So this is the length axis, and this is the operational takeoff weight. Here, around here, we get this point, and it is between 8 and 900 feet. Sorry, between 8,000 and 9,000 feet here, and we will get around 8,800 feet. So this is we get here from interpolation also. here. So we get the takeoff runway length is 8,800 feet. Then, because in the data before we have the maximum difference in runway centerline elevation is 20 feet, so we will just adjust for non-zero effective runway gradient, because there are some notes. Basically, for the landing length requirement also has its notes, and basically for two charts, for the takeoff length chart and for the landing chart, is has the conditions like zero wind, zero runway gradient. So if there is the runway gradient, we should have to adjust, because this is for zero effective runway gradient, the chart, and also for the landing length requirement chart. So because we have non-zero effective runway gradient, we should have to make an adjustment in the takeoff length requirement. So here the 8,800 plus 20 multiplied by 10, and we will get 9,000 feet. So the takeoff length for design is 9,000 feet. Then after we compare the landing length requirement and the takeoff length requirement, which the landing length requirement is 6,600 feet, and the takeoff length requirement has 9,000 feet. So we will use the takeoff length for the runway length, which is 9,000 feet.